Hello everyone, my name is Dinesh and I am from CSC department A section. This is my linear algebra and calculus PPT presentation. The topic is note on the normal form of a spatial stiffness matrix. From this topic we will understand about the spatial stiffness matrix normal form. That is the topic. In the finite element method for the numerical solution of elliptical partial differential equations, the stiffness matrix represents the system of linear equations that must be solved in order to ascertain an approximate solution to the differential equation. The stiffness matrix for the Poisson problem. For simplicity, we will first consider the Poisson problem minus delta square u equal to f on some domain omega subject to the boundary condition u equal to 0 on the boundary of omega. To discretize this equation by the finite element method, one chooses a set of basis functions phi 1 to phi n defined on omega, which also vanish on the boundary. One then approximates u approximately equals to u power h equal to u1 phi 1 plus so on un phi n. The coefficients u1 to un are determined so that the error in the approximation is orthogonal to each basis function phi I. And here is the equation: integral omega phi I into f dx equal to minus integral omega phi I delta square u power h dx equal to minus summation j into integral omega phi I delta square phi j dx into uj equal to summation j into integral omega delta phi I into delta j dx into uj. The stiffness matrix is the n element square matrix A defined by aij equal to integral omega delta phi I into delta phi j dx. By defining the vector f with components fi equal to integral omega phi I f dx, the coefficients ui are determined by the linear system au equal to f. The stiffness matrix is symmetric, that is aij equal to aji, so all its eigenvalues are real. Moreover, it is a strictly positive definite matrix, so that the system au equal to f always has a unique solution. For other problems, these nice properties will be lost. Note that the stiffness matrix will be different depending on the computational grid used for the domain and what type of finite element is used. For example, the stiffness matrix when piecewise quadratic finite elements are used will have more degrees of freedom than piecewise linear elements. The stiffness matrix for other problems. Determining the stiffness matrix for other PDE follows essentially the same procedure, but it can be complicated by the choice of boundary conditions. As a more complex example, consider the elliptic equation minus summation kl partial differentiation of a power kl partial differentiation of u with respect to x1 xl with respect to xk equal to f, where a x equal to a power kl into x is a positive definite matrix defined for each point x in the domain. We impose the Robin boundary condition, that is minus summation kl vk a power kl partial differentiation of u with respect to xl equal to c into u minus g, where vk is the component of the unit outward normal vector v in the kth direction. The system to be solved is summation j into summation kl integral omega a power kl partial differentiation of phi I with respect to xk into partial differentiation of phi j with respect to xl dx plus integral delta omega c phi I phi j ds into uj equal to integral omega phi I f dx plus integral delta omega c phi I g ds. As can be shown using an analog for Green's identity, the coefficients ui are still found by solving a system of linear equations, but the matrix representing the system is markedly different from that for the ordinary Poisson problem. In general, to each scalar elliptic operator L of order 2k, there is associated a bilinear form B on the Sobolev space h power k, so that the weak formulation of the equation Lu equal to f is b into u comma v equal to f comma v for all functions v in h power k. Then the stiffness matrix for this problem is aij equal to b phi j comma phi I. Practical assembly of the stiffness matrix. In order to implement the finite element method on a computer, one must first choose a set of basis functions and then compute the integrals defining the stiffness matrix. Usually the domain omega is discretized by some form of mesh generation, wherein it is divided into non-overlapping triangles or quadrilaterals, which are generally referred to as elements. The basis functions are then chosen to be polynomials of some order within each element and continuous across element boundaries. The simplest choices are piecewise linear for triangular elements and piecewise bilinear for rectangular elements. The element stiffness matrix A power k for element tk is the matrix aij power k equal to integral tk delta phi I into delta phi j dx. The element stiffness matrix is 0 for most values of I and j, for which the corresponding basis functions are 0 within tk. The full stiffness matrix A is the sum of the element stiffness matrices. In particular, for basis functions that are only supported locally, the stiffness matrix is sparse. For many standard choices of basis functions, that is piecewise linear basis function on triangles, there are simple formulas for the element stiffness matrices. For example, for piecewise linear elements, consider a triangle with vertices x1, y1, x2, y2, x3, y3 and define the 2 by 3 matrix. And it is D equal to x3 minus x2, x1 minus x3, x2 minus x1, and second row is y3 minus y2, y1 minus y3, y2 minus y1. Then the element stiffness matrix is a power k equal to d power t into d by 4 area into t. When the differential equation is more complicated, say by having an inhomogeneous diffusion coefficient, the integral defining the element stiffness matrix can be evaluated by Gaussian quadrature. The condition number of the stiffness matrix depends strongly on the quality of the numerical grid. In particular, triangles with small angles in the finite element mesh induce large eigenvalues of the stiffness matrix, degrading the solution quality. And that's and it is my topic for linear algebra and calculus, Python, linear algebra and calculus, PPT presentation, and